I'm gonna go and get started. People can keep trickling in. That's fine. So we're gonna be talking about scheduling now. More specifically, scheduling is a problem that the kernel has to deal with, specifically regarding processes. Right. So, for example, when we were talking about processes last week, we looked at we ran top on my terminal and saw kind of the list of all the processes that were either running or were waiting in order to actually get a turn to run on the CPU, right? So, and then maybe typically there's something along the lines of 200 or 250 odd processes, and I'm on a 4-core machine. So, how exactly? How do we be smart, or how does the operating system kernel be smart about exactly how it schedules or how it decides which processes get to go and get allocated to these 4 CPUs, so that we're maximizing efficiency of our computing resources, right? And so let's talk about that. So we can kind of work our way from the ground up, right? So we have, just like, say, we have our list of, let's just say, 200 processes that need to be spread out amongst 4 cores. Actually, it'd be easier if we just said, so let's just say we have 200 processes and we only had 1 core. So this will make it a bit easier to build up to the concept of how scheduling actually works. So we have 200 processes in 1 core. How does the operating system kernel decide which process goes next and get some time to execute on our single CPU? So what if we just started simple and just say, okay, we have this list. Let's just pretend that our list is a queue, right? So whichever process arrived in our queue of processes first, let's just take that one. Let's give it some time on a CPU, and let's just call that. Let's just say it gets 10 nanoseconds of time, for example. Just making some preliminary assumptions here. So let's assume we have a queue. All the processes go into this one queue. We remove from the top of the queue the process that's been waiting in line the longest. That gets to execute for 10 nanoseconds. And then it goes back into the queue if it still needs more time, if it's not completed yet. If it is completed, then we'll just toss it, and it doesn't go back into the queue because it doesn't need any more CPU time, right? So let's just imagine we did something like that. Okay. The problem with doing something very simplistic like that is that we have what are called processes that might just run forever, or processes that take a long time. Okay, and this is in contrast with, there are also processes that take a very short amount of time. Sure. Okay, that's also a very good point. We also have processes that require kind of like more priority, or we need to execute those because those are very important processes, right? So our queue example doesn't do a good job of balancing that, right? Because, for example, in our list of 200 processes, if all of a sudden some very important process comes along that needs to be executed in a timely fashion, if we just have a queue data structure that's actually holding all of our processes, that process needs to wait all the way until every other process has had its turn, and then it gets to run, right? So priority is very important. Again, not all processes are equal, right? So some are way more important than others. For example, the operating system itself is just another program. So actually it includes itself in the scheduling problem, right? So it needs to be able to kind of schedule itself amongst all of the other processes. And the operating system needs to run, way more often than, Slack or your browser, for example, because it's way more critical to the running of your machine. Right, so that's an important tenet, that again, not all processes are equal. Some have much higher priority than others. Some things that might determine priority. One thing, for example, is responsiveness. Right, so that's one metric by which we can kind of determine priority of processes. And so, what do we mean by responsiveness? Well, that means that, as soon, so on your machine, you either have a mouse, or you have a trackpad, whatever, peripheral for actually moving a cursor around. So right as you move your cursor, you get a response from your machine. You see the cursor move. And immediately, for example, I can go and like click into Slack and just immediately start typing, and you'll see the text, propagate in Slack or in your terminal, in your browser, or whatever. Right. So that is an example of responsiveness. These particular actions, moving the cursor, typing some text into Slack, these all require high responsiveness. So there are processes that literally just wait. So for example, there's like a process whose sole job is literally to just wait for mouse movement on the cursor peripheral. And right as that happens, it needs to wake up, it needs to get immediately scheduled on the CPU so that it can start executing and following through on the user's inputs. Okay, so that is an example of a process that requires high response time. Same, of course, with whatever process is in charge of handling the receiving of text when you type into a terminal or Slack. Okay, so responsiveness is very important. And if we just had a queue data structure, well, that wouldn't fly, right? Because then all of a sudden, what the user would see is they would move the cursor, and then the first time the cursor actually moves in response to the user's input would be after every process that was before it got to execute, which would make computers very hard to use, right? Or at least really hinder the user experience. So what's nice about these responsive tasks is that usually they're very short, right? So we'll like type something, so we type a single key, for example. That process that is responsible for responding to that needs to wake up, register that key press, and then it can immediately go back into sleep or waiting. Okay, so this job, I'm going to use kind of job and process a little bit interchangeably. So this job of registering the key press might be a very quick job. Okay, because there's not much to do, right? Compare that to, for example, the process that actually maintains the loop of like your terminal or your browser. Like that kind of just sits in the background, even though the browser itself is not updating very often, right? It needs to update when a user responds to it, right? Or when a user starts typing some text or starts interacting with the browser. But when there's no need to update anything, it just kind of sits in the background, and that particular process runs for a long time, but doesn't need to update very often, right? So that's kind of in contrast to a very quick, kind of short job that requires high response time. So we have this contrast between short, quick jobs and long-running jobs that perhaps don't need to update very long. So what if we could somehow augment our queue with being able to prioritize short jobs versus long jobs? So, we have processes in the queue, and let's assume that they know how long they each need to run for. And a short job comes along, we could perhaps maybe just shunt it, past all of the processes that have a longer response time or have a longer running time than that short job. So then all of a sudden, that particular short job only has to wait for the other short jobs in front of it before it gets executed. So that would help with response time, right? But the problem with this example now is, so that we've kind of made a step towards solving responsiveness, but now all of a sudden, all the long-running processes might not get any execution time at all. If, for example, we got ourselves into a case where we were just, a whole bunch of short responsive processes or jobs were coming in to our process queue, and they would, just be stealing processing time away from the long-running jobs. And even though we did say that perhaps the long-running jobs, might not need a lot of updating time. That's not to say that, you know, we could just leave them there forever and never get any CPU execution time allocated for them, right? So another thing we kind of want to balance is fairness. Is, you know, we kind of want to be partisan about, you know, the fact that, you know, we do want to give every single process some attention, right? We don't want any processes just sitting in the back of the queue forever and ever being totally neglected, right? So that's another thing we would need to balance is kind of fairness of all the processes. So we kind of want to ensure that every process gets some execution time. The other problem with this particular augmented kind of queue idea is that we actually don't know when jobs come in how long they're going to take. Like we actually have no idea. And the operating system kernel can't tell because it can't read the future. Because if it did, well, that'd be pretty crazy. And the implications of that would be, anyways. So our kernel cannot read the future. So when a job comes in, we actually have no idea from the get-go that will be a short job. So there's actually no way for us to go and say, okay, the job that came in is short, let's punt it to the top. Again, we have no idea. And same with a long-running job. Like a job might come in, it might end up being a long-running job. It might be closed early, even though, you know, when it ran normally, that job might be a very long-running job. You know, there might be some error in it, and it might exit, you know, abnormally, such that it turns out to be a short job, right? So again, the kernel has no way of knowing that, and so we can't go and say from the get-go that, oh, we can put this in a certain place in our process queue. Okay, so this augmented queue idea of putting short jobs first actually is just not feasible whatsoever. So what if we kind of took a step back and instead of just doing like a normal queue, we just so let's go and run with the fairness idea for a little bit, right? So if we wanted to maximize fairness amongst all of our processes, what if we just did a round robin sort of deal, right? So again, start at the top of our queue, give every process. Oh, I'm sorry, I already did that. Okay, I was supposed to say initially with the first queue idea was that we would remove from the top of the queue and that process would run until completion, and then it would and then the next process would go. Sorry. So the round robin idea was basically what I described in the first place of we loop through our entire queue, give the first process a time slice of say 10 nanoseconds, put it back at the queue at the end, and then just keep cycling through every single process. So that would achieve maximal kind of fairness, which is nice. So then all of the long-running processes at least get to see the light of day for a little bit. Or actually, they get to see the light of day every cycle. But then again, as we said, the problem with maximizing fairness in this case was that, again, we can't go and just assume every process is equal, because again, they're not. So we do want to give some execution time to those processes that perhaps don't need high priority, but again, that doesn't mean we're going to just stick them in the broom closet and never see them again. So we kind of want to balance priority with fairness, right? So how can we kind of come up with a scheme or a data structure that allows for responsive processes to get execution time on the CPU right as they come in, while at the same time not just leaving the long-running processes behind. So kind of the idea then going from there is, what if we had every process that came in, we just automatically assumed it had high priority. So for example, we have a queue that comes in, processes come in, land in a queue, and then we do what we had said initially. So there's a queue that removes from the front of the queue, gives that process some time slice execution time on the CPU. And then if that process finished, that means it was a short job, which is great. So it was a short, most likely job that required high responsiveness or quick response time. So, we treated that short job accordingly because we gave it initially high priority and responded to it in a timely fashion. And then instead now also assume that a long-running process comes along. We initially give it high priority, so it's executed along with all of the other short jobs initially, but then we give it the same time slice that the short jobs got. Okay, so we give it 10 nanoseconds, but then we figure out that, this process needs more time than this. Now, when that happens, and we get a process that for that given time slice didn't complete, let's put it in a lower priority queue. Okay. And the processes in the lower priority queue will now only ever get any execution time when there's no processes in the higher priority queue. So what we're coming up with is this tier is this data structure that's comprised of a number of tiered queues, where the different tiers represent different priority levels. So again, the topmost tier or the topmost queue is the highest priority. As long as there are any processes in that highest priority queue, we're going to go and remove from that and keep giving processes in there execution time, because those are the ones that just came in. So we're going to assume that they require high response time. And we're just going to assume that of every process that comes in, regardless of whether they actually require that responsiveness or not. So if a process that doesn't require high responsiveness, but just, ends up sitting there for a long length of time comes in, and we give it some execution time and then it's not complete, well, then it wasn't a short responsive job. So what we can do now then is put it in a lower priority, because it's not short and it needs to keep running. So typically you're not going to get processes that are high priority that also take a long time, typically. Obviously sometimes it does happen, but we're going to kind of treat that as an outlier in the case of our particular scheme. So the long-running jobs that don't complete in the highest priority queue now get shunted to the next priority. And now the next time that they get to actually see any CPU time is when there are just no processes in the higher priority queue. And so we'll just have a bunch of these tiers culminating at a lowest priority queue, where that will literally just, the processes that sit in there, will eventually, if they make it to the very bottom, then they will kind of, by default, not see the light of day for a very, very long time, right? But that's not to say that we didn't give them any execution time, because again, when they came in initially, they got that execution time. They got execution time all the way down until they hit that very last queue. If they made it to the very last queue, that means that for every hop that they made down, they got execution time, right? So we don't move any processes lower unless they get some execution time. So this scheme that we kind of came up with has a name, and it's a very kind of classic solution to this problem of scheduling, of balancing things like fairness and responsiveness, and making sure that the short processes have a quick turnaround and stuff like that. So it's actually the concept of it borrowed a lot from whatever the study of logistics is called. It's like management science or something like that. I think it's something like that. I think that might be one name. You made that up, right? I think I'm thinking about management science or something like that. Like thinking about what? I'm looking this up. Anyways. But so yeah, this idea of this particular data structure, it's called a multi-level feedback queue, borrows a lot of concepts from management science and kind of how to efficiently schedule stuff like distribution lines and stuff like that. Stuff that I don't know much about, so I'm not going to pretend like I do. Okay, so if we wanted to kind of visualize it a little bit, it might look something like this. So we start off at the top with high priority queues, and this queue is numbered 8. Although it'd probably make more sense to number this as Q1 and then 2, 3, 4, 5, 6 all the way down. But anyways, so the jobs will come in, they'll populate the highest priority queue, and then this will get popped off onto our CPU. And again, if it finishes, then great, B is done. We'll just remove it. So it'll just get shunted, and then A gets to go. And let's just say A runs for 10 nanoseconds, and it doesn't complete. At which point now it'll get removed from this queue and then go over here. Okay, and let's just say no other processes came in. Then so Q8 is empty, and now the scheduler will now go and look in Q7. So Q7 will find A, and then A will get it removed again and get more CPU time. So another kind of slightly important detail with regards to the multi-level feedback queue is that different queues have different time slices associated with them. Okay, so the highest priority queue will actually have the lowest or the smallest time slice associated with it. So we gave Q8 10 nanoseconds. Okay, then Q7 might have a time slice associated with it of, say, 20 nanoseconds. And then as you go down, these time slices will increase. So if we ever get to a point where we're running processes off the lowest priority queue, this might be like, for example, 5 ms, for example. Like a much larger time slice than all the queues previously. Because the logic there is, if we've actually made it all the way to the lowest priority queue and there just are no high priority jobs coming in, then we're pretty much we're pretty much in a state where, you know, your computer is just sleeping, and there's no new inputs coming in. At which point now we can use our CPU resources to go and work on these low priority queues, so we can run each of these for quite a while, comparatively. So in Q7, A might go and get, you know, whatever time slice is associated with Q7, so 20 nanoseconds. And if it keeps making its way down and nothing new comes along, then it will get like 30 nanoseconds and then 40 nanoseconds, for example. Right. Until some new process comes in from the top, and then all of a sudden the scheduler needs to go and jump back to the highest priority queue and execute whatever processes came in. So another important thing we want to talk about is what are called blocking processes. So imagine that some process comes along that needs this process in its execution. While it's executing, it needs to go and make an I/O request, right? So let's say it needs to go and fetch a file from the hard drive, right? While it does that, okay, so in order for the process to actually do that, it needs to be executing on the CPU. So our process comes along, it gets execution time on the CPU, and then while the CPU is executing it, it hits upon the instruction saying, hey, I need to go and fetch this file from the hard drive. Okay, so that process will now make that request, and the kernel now needs to go and actually perform that request of fetching the file from the hard drive. And so now that process is in a blocking state because it's now just waiting on some I/O operation. It's waiting for that file to be retrieved and returned to it. Okay, so in that particular case, and you know, that process will still have some CPU time left, right? Let's say it only took up 5 nanoseconds out of, like, say it's 10 nanosecond time slice. So halfway through the 10 nanosecond time slice, it performed the blocking operation, and now all of a sudden it has 5 nanoseconds that there's just no point in wasting, right? We could keep giving the blocking process that extra 5 nanoseconds, but we know it's in a blocking state. It's just waiting. So there's actually no point in giving it that 5 nanoseconds. So what we're going to do in that particular case is we're actually going to put it into a different queue that is actually, quote unquote, even higher than the highest priority queue. And this is the blocking queue. So this is a queue specifically for processes that have gone into a blocking state, right? So if we say B was received 10 nanoseconds, so B received 10 nanoseconds on the CPU. Halfway through, it got into a blocking state because it had to go and make an IO request. Then the scheduler will go and put B into the blocking queue. And the blocking queue will actually have an even higher priority, right? So as long as there's something in here, we'll always go and check the blocking queue to see if the IO request that B made returned. And we want to check that as often as possible because we don't want to leave processes in the blocking queue for any longer than they have to be in there. So then when the IO request comes back for B, and it no longer needs to be in a blocking state, we'll remove it from the blocking queue and put it back in the highest priority queue so that it can now wait its turn to go in and get CPU execution again with whatever file that it got back that it now needs to execute on. So this is kind of the whole kind of general scheme. And so what you guys will be doing for this particular, for today and the rest and tomorrow, is implementing kind of a simulation of the scheme, of this data structure, right? If you just think about it, really this entire thing, this entire multi-level feedback queue is just a large data structure that comprises a number of moving parts. So that's to ensure the IO complete. Well, the IO will complete, assuming no errors occur, and that's a different issue if it does. But yes, so B will just go into the blocking queue and wait for the IO request to come back. Once it comes back, once it comes back, the scheduler is checking the blocking queue often. So there shouldn't be a large span of time between the request comes back and the scheduler notices that. So right as the scheduler notices that B is no longer needs to wait on its IO request or that its IO request came back, it'll just go and put it back in the highest priority queue. But why is it in the highest? So why is the blocking queue the highest priority queue? Or why does B go back in? So blocking is the highest priority queue, again, because we don't want processes to sit in there for a long time, right? We want to be efficient about if process has to go into the blocking queue, we want to leave that blocking queue almost as soon as it is no longer blocking, right? So if we imagine instead the blocking queue was at the bottom, right? So for example, if B ran into a blocking operation, and then it went into a blocking queue that was at the very bottom, well, when are we ever going to check those, right? Almost pretty much when your computer is totally idle is when you'd get around to that. So B would then be sitting in the blocking queue for a really, really, really long time, even though it's ready to go, right? So we want processes that perform IO operations to respond to those IO operations as quickly as possible, right? So that's why blocking is actually considered even further up the priority list than it really wants to complete its task. It only has to wait on the right, exactly. Right, we want kind of fast responsiveness with regards to responding to IO operations or responding to any sort of hardware requests. Right, so for example, if we were to draw like we were to draw a parallel for this. So imagine again, we wrote some code in C that made a malloc call, right? So then we execute our file. It gets allocated some time on the CPU by the scheduler in order to actually run our file, for example. That makes a malloc call. As the CPU executes our code, it runs into the malloc call instruction, and that's blocking, because our process needs to block and wait for the request from our process to get to the kernel. The kernel needs to fulfill that malloc call and come back with the pointer to the memory, right? We want that to come back as fast as possible, so that, you know, there's no extra overhead of being like, oh, we can't, you know, we got the memory back, but we can't act on it quickly, right? We want to be able to use that resource we got back from the hardware as quickly as possible, if that makes sense. Otherwise, then it would be very undesirable to make any sort of blocking I/O operation, right? And then we would just try to limit that as much as possible, because it's just not efficient. But that's not really how we want our CPU or our machine to operate, right? That's why blocking processes technically have the highest priority. So you'll be happy to know that this particular sprint will be done back in JavaScript. And this is because, well, it's very much like the data structures. It's very much like the data structures sprint. So you'll go and implement a couple of different pieces. Actually, so let's just go look at the code for a bit. So the way this will work, there are multiple kind of classes that you'll need to go and implement. So for example, there's a process class. So, yeah, okay. Whatever. So there's a process class, and this class represents a single process, right? So there are a whole bunch of processes that will be represented by this class that will come in, and the scheduler will need to execute them for some allotted time, right? So for example, each process has a PID, has a queue that it belongs to, and this will be a reference to whichever queue it's currently in. And each of these will also have a CPU time needed variable. So this is, and this is why I say this is a simulation. This is not entirely realistic. The simulation that you guys are implementing is not completely true to life, right? Because again, as I was saying at the beginning, this is not possible. This is not actually a variable that would actually exist on an actual process, data structure, right? Because again, each process doesn't know how much time it actually needs. But for the purposes of this repository, or for this sprint, we're just going to have this to dumb it down a little bit. But again, just remember that this is not real. This is not actually feasible to have every process know exactly how much time it needed. If it did, then we could just fall back on that idea that I mentioned at the beginning of, we could just have a single queue and just punt all the all the processes that had a low number for CPU time needed to the front. And then same thing with blocking time needed. Every process will have this variable, and every process might have the possibility of shifting into a blocking state. So you'll see that if this is a non-zero number, then this process will need a certain amount of time on the blocking queue. And then state change represents every process coming in if there's two different states, right? So there's the normal kind of running queues. So the normal running queues, which are the normal CPU priority queues, and then there's the blocking queue. So this state change variable represents if this particular process has jumped between the running state and a blocking state. So all the function skeletons are here with the parameters, along with some comments on what each needs to do. So you'll fill these out and get them to pass the particular tests associated with each class. So Q is the Q class. It has an array of all the processes that it stores. Each queue has a different priority level, which is assigned to it by the scheduler. And then Quantum is the time slice I was mentioning that's associated with each queue, right? So we said, for example, in our example, we were talking about the lowest priority, or sorry, the highest priority queue has the lowest quantum, has the smallest time slice. Okay, so this also gets assigned to each process, to each queue by the scheduler. And then quantum clock, then you can think of as the counter, because when the CPU actually starts executing a process from this queue, we'll increment this counter for as long as the CPU executes it for, until it reaches the associated quantum, until it reaches that threshold. So once it reaches this threshold, then we check to see if the process that was running from this particular queue is done. If it is, then that process is done. Otherwise, if it isn't, right? So that means then that the process got the allotted time slice as per this quantum variable. But now if we check to see that that process is not done, that's when we go and move it down to the next priority queue. And then queue type represents if this is a blocking queue or this is a running queue. And again, running queue is every queue that's not the blocking queue. And then lastly, the scheduler kind of oversees all of this. So with the scheduler is the one that keeps track of the actual time, the clock as it's running. It initializes a blocking queue, and then it initializes a bunch of running queues, a list of, or an array of a bunch of running queues. And it'll assign each running queue a different time slice. So one last thing that we should probably talk about before you guys go and get started on this. Actually, let's go and look at main.js first. So when you go and actually npm start, it will just run this main program. And inside this main program, it just instantiates a new scheduler, and then it adds 100 processes to the scheduler. And then each process has a 25% chance of being initialized as a blocking process. So on average, you're going to get 75 running processes and 25 blocking processes, which and the blocking processes will have to be dealt with accordingly. And then all of these get added to the scheduler, and then we run the scheduler, and it literally just runs and chews through these 100 processes until it's all finished, ideally. So again, another aspect of the fact that this is very obviously a simulation and not the real thing is that we only give it 100 processes. So as the scheduler is running, no new processes are coming in, which is not very realistic, right? But that would be a hard thing to do, to say, okay, initialize our scheduler with 100 processes at the beginning, and then as it's running, we might be injecting a bunch of new processes into it. I couldn't really figure out a way to do that. So that's another unrealistic point for our simulation, right? Again, no new processes are coming in. So the scheduler just chews through the 100 processes that it was initialized with. Okay, and then last point of business is how a process communicates with its parent queue, and how a queue communicates with the scheduler, right? So for example, the queue needs to communicate with the scheduler in the case when the process that it's currently running, or the process that was removed from it most recently was running, and that it didn't complete in the given time slice, right? In that case, the queue needs to go and tell the scheduler, hey, go and put this process in the next priority queue, right? Because the queue doesn't know about the processes, or sorry, the queue doesn't know about the queues in front of it or below it in priority, right? Any particular, like the highest priority queue doesn't actually know it's the highest priority queue, right? So it's the scheduler that actually supervises all of that. And so it's only the scheduler that's able to go and then receive the process that didn't complete and move it and enqueue it in the queue that is after the process is after the queue it just ran on. Sorry, keep mixing up my terms. So if we look here in this constants file, so here we have a bunch of different interrupts. Okay, so these interrupts are important because you'll need to dispatch these in certain cases in order to notify the correct class. Either it might be queue, it might be scheduler, of something that happened. So like the case that I was just talking about, if the queue was running a process and that process didn't complete in the allotted time slice, that queue would now go and dispatch this lower priority interrupt to the scheduler. And the scheduler would receive that, and then it would execute the logic of taking that process and putting it in a lower priority queue. And then we also have process ready and process blocked interrupts. Those are for moving processes between the blocking queue and the ready queue and the running queue, right? So when a process is running normally and it becomes blocked, it will then that queue should dispatch the process blocked interrupt to the scheduler so that the scheduler can then move that process to the blocking queue and vice versa. When a process in the blocking queue is no longer blocking, it'll dispatch this process ready interrupt. And the scheduler will take it and put it back in the highest priority queue. So that's kind of roughly how communication is facilitated between the different classes. With some other constants here, CPU type, strings, and then number of priority levels. So we'll actually, for our simulation, we'll only have 3 queues plus the blocking queue. So 4 queues in total. Although I should say more realistically, like I know in this particular scheme or this particular data structure used to be used by Linux. This was the data structure that backed the Linux scheduler in one earlier iteration of it. It doesn't actually anymore. But I know in that particular case, I believe there's something like 250 priority queues. So the scale of this here is of course way smaller. And then lastly, there's the tests. So there are test suites for every one of the classes. But do be aware of the fact that, and you should definitely read through some of these, but for example, so some of these tests, so for example, in the process test suite, it might test some behavior that relies on, for example, the queue. So like, for example, here, this execute blocking process function. So this particular function in the process test suite actually relies on some functionality that the queue relies on some functionality to be implemented on the queue class, right? So if you start and finish up the process class, that doesn't necessarily mean that you'll get all the tests passing, right? And this is kind of a consequence of the fact that all of these 3 classes, process, queue, and scheduler, are really intermingled with each other, right? So that's kind of the main difference between this particular sprint and the initial data structure sprint that you guys got a few weeks ago. With the initial data structures sprint, you were just implementing modular data structures that really had nothing to do with each other, and so the tests could be really and entirely self-contained. But with this one, you implement the process class, and that is then used in the queue class, and then the scheduler oversees both of those. And so there's a lot of interdependency between these 3 classes. So just keep in mind that, again, if you just finish the process class on its own, that's not necessarily going to go and get every single test passing in the process test suite. So you'll want to read through the tests, both as because it'll clue you in on exactly how each function should be implemented, as well as you read it and see, oh, this utilizes a queue function, So of course this isn't going to work yet because I haven't implemented anything in the Q class. But yeah, that's about it. Down here, there's a big pseudocode block for kind of the entire algorithm of what the multi-level of the multi-level feedback queue running. Some stretch goals that I don't know if anyone will get to it again because of the condensed schedule, but if you get there, please do give them a shot. But yeah, that's about it. Again, this is done in JavaScript, and typically, and this has historically been the sprint that was the first foray back into JavaScript after students had C. And so students always feel like JavaScript is way easier after working in C for a few weeks. Cool. Let me link that. But yeah, other than that, that's about it. Setup again is back to how you did in JavaScript. So you'll want to npm install. You'll run npm test to actually execute the test suite, et cetera, all that good stuff. And then, okay, so I'm not going to have a Q&A for this evening. So I want you guys to kind of keep working through this this sprint through the evening. So you have the rest of the day to just keep working on it, except for, I guess, PM stand-ups with your respective PMs at 4. But other than that, you just get time to work on this. And then I think tomorrow morning at the usual lecture time, we'll just do the Q&A at that time, because I'm pretty much done lecturing on the topic of scheduling. So tomorrow morning we'll have a Q&A on this, and then solution lecture at the end of day tomorrow. And then we'll have Friday for the sprint challenge. So that's the planned schedule. Does anyone have any questions? AJ is raring to get started. He's so eager to get back into JavaScript. All right, cool. So yeah, again, you have the rest of the day to work on this. Q&A will be tomorrow, so I will talk to you guys then. And if I don't talk to you guys again today, then have a good night, and I'll see you guys tomorrow. All right, thanks, guys.